In this video, we discuss charge disk. Consider a circular disk of radius r bearing a constant surface charge density of sigma. Calculated field strength at a point P on the axis of the disk at a distance z from the center of the disk. Two infinitesimal symmetric area elements about the center of the disk create two infinitesimal fields at point P. Upon inspection, we observe that the sum of these two vectors is orthogonal to the disk. This is because their horizontal components have the same magnitude but opposite direction. A ring is composed of infinitely many pairs of infinitesimal areas. The horizontal components cancel out for each pair of vectors, and the resulting sum is a vertical vector, which is the field for the ring. This vertical vector is the sum of all fields due to the infinitesimal areas on the ring shown. Notice that the field at point P changes depending on the radius of the ring, and the sum of all these fields due to tiling rings on the disk creates the entire field at point P. Again, consider a circular disk of radius capital R bearing a constant surface charge density of sigma. Calculate the field strength at the point P on the axis of the disk at a distance z from the center of the disk. We're going to imagine the disk is charged uniformly with positive charges in here. So looking at this disk and point P, the distance from the origin from P is z, and the radius of the disk is capital R. We are also planning to use rings of width delta R and radius little r on this disk. Now, the center of the disk has a distance little r from any point on the ring, which if we put an infinitesimal little charge on the disk, it's going to be of distance r from the center, and the center is also has the distance z from the P. So the distance between any infinitesimal charge, you can call it dq or delta q from the point P, is going to be square root of little r squared plus z squared. Um, and this distance is crucial in finding the field that this little infinitesimal charge creates at P. We call that field E sub dq. Now, field E dq is due to the charge delta q at distance square root of r squared plus plus z squared. Therefore, the magnitude of this field is going to be k delta q divided by the distance, which is square root of r squared plus z squared to power 2. Next, let's find the magnitude of vertical and horizontal components of E sub dq. To find the vertical component of E sub dq, you continue the line that you drew from center of the disk to P onward, and then you drop a perpendicular at the end point of the vector E sub dq. And we call that E sub dq vertical. And similar thing happens with E sub dq horizontal, and we call it E sub dq edge, which is a horizontal line, and you drop a perpendicular. To find the magnitude, basically look at the triangle that is formed between the E sub dq and E sub dq vertical and the triangle below it. They are similar, so the ratio of the magnitude of E sub dq vertical to E sub dq is equal to z over square root of z squared plus r squared. And so multiply that ratio by what you found is the magnitude of E sub dq, and that will give you the magnitude of E sub dq vertical, which after cleaning up is going to be k delta q over times z over um, parentheses r squared plus z squared parentheses close to power 3 half. So you might ask, what happens to the horizontal component of E dq? We have to remember that there is an symmetrical piece of charge, a small infinitesimal piece of charge that actually the field that other symmetrical component creates has the same horizontal component in the opposite direction, has the same magnitude of horizontal component in the opposite direction. And so the horizontal components, pair by pair, cancel each other out. So the sum of the two fields resulting from the two infinitesimal symmetric charges is going to be a vertical vector whose magnitude is equal to twice the magnitude of vertical components of each field. Let's divide a ring into two and many infinitesimal charges. The sum of the fields is a vertical vector. All horizontal components are going to cancel. Notice that in the sum, r and z are constants, but infinitesimal charge delta q equal to sigma delta area, and area depends on n. Delta area is equal to r delta theta delta r. That is, delta charge is going to be sigma r delta theta delta r. Delta theta depends on 2n, and it's equal to 2 pi divided by 2n. After summing over delta theta, which is the only non-constant, we end up with sum from 1 to 2n of delta theta is equal to 2 pi, and the magnitude of the field due to the ring is going to be computed as 2 pi k z sigma delta r divided by quantity r squared plus z squared to power 3 half. Using Calc 1, we can tile the disk into m many rings, sum the m fields due to the rings, then take the limit as m goes to infinity to get the integral from 0 to r 2 pi k sigma z r dr over quantity r squared plus z squared to power 3 half. Then we do a u substitute, u equal to little r squared plus z squared. Du is going to be 2r dr, little r's. Bounds change from 0 and capital R to z squared and z squared plus capital R squared. The resulting integral is integral from z squared plus capital R squared plus z squared of integrand pi kz sigma du over u to power 3 half. After taking the integral, we end up with 2 pi kz times 1 minus z square root of r squared plus z squared. In the beginning of this video, we computed the magnitude of the orthogonal component of each infinitesimal area element on the disk. This magnitude is kz dq over parentheses r squared plus z squared to power 3 half. The area element in polar transformation is dA equal to r dr d theta, which gives dq equal to sigma r dr d theta. Replacing dq by this new sigma r dr d theta, we quickly realize that the sums that we computed throughout the video is going to be a polar integral, integral from 0 to r, integral from 0 to 2 pi, kzr over quantity r squared plus z squared to power 3 half d theta dr, which is much easier to compute. So if you are in Calculus 1, you have to watch the entire video. But if you